You. I'd like to start today by thanking all of you for attending the second day of this excellent conference. I'd like here to mention that the organizer committee did a marvelous job, really, and I'd like to compliment each one of them. Dr. Ghaddar has been a great host. We all feel happy and welcomed. With that, I'd like to introduce our first keynote, third keynote, first for today. And it happens to be Bill McQuade, who's very close to me. We work very closely in ASHRAE, and Bill is considered to be, one of my best friends. So I'm very happy to do the introduction, Bill. Bill McQuade is the Executive Director of Global Industry Relations and Regulatory Policy at Johnson Controls. He's been there for 25 years, working for the York International / Johnson Control organizations in various technical and managerial positions, ranging from research engineer to senior management position related to the strategy application of advanced technology and research and development efforts. Bill, all his degrees, master, bachelor, master, and PhD, actually MBA, are from Penn State. And he's been working with ASHRAE for many years. Also, he is on the board of director for ASHRAE. Bill is very active in ASHRAE. He had one of the big important committee on MTG for flammable refrigerants, industrial assessment on the refrigerants issues. Bill is a truly professional person, has a lot of knowledge. He's been attending all international meetings, so he has a lot to tell us about those meetings and regulations and so on. Bill, we're very happy to have you here. Thanks for being part of this conference. Would like you to come to stage. Thank you.
Thank you. Good morning, everyone. I want to first say how honored I am to have been invited to come and speak here. I'm so impressed with Lebanon as a country, and in particular AUB and the students that I've met here. Fantastic, very knowledgeable, very confident in what they know. So thank you for allowing me to come here and be with you today. A little bit about my background, and this is my contact information if you want to contact me on any of these topics afterwards. I've worked for the York and Johnson Controls companies for 25 years. It's actually my 26th year. I spent most of my time designing chillers. For many years I was in our R&D organization, and I actually ran that for a while. But since 2009, 2010, I've been spending a lot of time on regulatory issues, particularly around refrigerants and energy efficiency. And I've been attending the Montreal Protocol meetings since 2009 also, and helped with our industry's kind of mission to that organization in the development of the Kyoto Amendment to the Montreal Protocol. Also, I've been very involved in regulatory efforts in Europe on F-gases and energy efficiency, and of course in the US. I spent a lot of time in Washington dealing with the regulations there. So I have kind of a global experience in regulations, and today in my talk I'll talk a little bit about kind of what the regulatory landscape is in various parts of the world. That can be very complex, so I'll try to break it down into more simplistic terms and talk about what I'm seeing happening in different areas and the lessons that we can take from that. I'll also talk about the importance of, with the new generation of refrigerants, of safety standards and building codes, and how those are going to really pace the adoption of these new solutions as we go forward. I wanted to make sure I spend some time talking about the importance of energy efficiency. There's a tendency when you talk about refrigerants to think about the global warming potential of those refrigerants alone, when really if you look at the total impact of equipment over time, energy efficiency is an extremely important aspect of that, and you can't just look at the global warming potential of the refrigerant. You have to look at how that refrigerant performs in the piece of equipment and that overall impact. So I'll talk a little bit about that and try to give you a perspective of how important that energy efficiency is versus other aspects of equipment emissions. Then I'll talk about how the industry is evaluating refrigerants, and I'll give you some charts that will help you understand some of the alternatives they have for refrigerants like 134A and for 410A, and which ones seem to be emerging as the next alternatives. And lastly, I'll talk about how manufacturers, what manufacturers consider as they select refrigerants, to give you an idea of maybe what the thinking is of the manufacturers as they come out with new products. So the first part of it is really the regulatory landscape, and this is going to be a little bit of a slower progression, but I think I could give you a perspective as you see things happen, maybe what's behind them. So what are the factors that drive refrigerant regulation? And of course, ozone protection is what drove the last change, but people don't maybe understand that there are certain regions, including this one, that transition from CFCs and HCFCs hasn't been completed yet. So some of the posturing that you see in the international agreements around transition timing has to do with the fact that, particularly in the Middle East, they still haven't exited R22 in many markets. And their perspective when it comes to looking at alternatives is different than in Europe or North America, where they're considering 410A, for instance, as the refrigerant they're trying to replace. R22 is really still the refrigerant that they're looking at replacing. And there wasn't really a good direct replacement for R22 in the HFC realm, let alone some of the low GWP options. So that definitely, the fact that there's still many countries in the world that are transitioning out of R22 affects the timing and the desire for other countries to go forward. Climate concerns, obviously the shift away from HFCs is focused on climate, and you have to have the obligatory polar bear whenever you talk about climate and sitting on an ice cube. But certainly global warming is a very important concern in our industry. I think our industry over time doesn't get enough credit for the work that we've done, particularly around energy efficiency to reduce emissions, but that's certainly driving. And the other two factors that people don't really think about, but I'll tell you, being involved in this process for many years, the intellectual property around the refrigerants absolutely is a driver in the regulation that you're seeing, and particularly the urgency to move forward. Many of the refrigerants that we use today commonly are no longer covered by intellectual property. So you see low-cost manufacturers cropping up in places like China and India, and that has reduced the market price for refrigerants over time and kind of cut the margins on some of the producers. And that is something that new refrigerants that have some intellectual property rights to them definitely is something that is causing those companies to want to see a change in refrigerants happen very quickly. And the last thing is regional preferences. And this is something where, for instance, in Saudi Arabia, there's a concern that the alternatives to R22 aren't good at high ambient conditions. And there is some truth to that in certain conditions, but some of that isn't warranted across the board. But there is a preference to not use certain types of refrigerants and others. Another example is in Europe, particularly in Northern Europe. There is a kind of a group of folks who are very into natural refrigerants, so CO2 and ammonia and propane and isobutane. They see it's almost a religion at times where they don't want to use any HFCs or HFOs because they feel they're not naturally occurring in the environment. So that flavors some of the regulation that we see in Northern Europe around their willingness to use some chemical solutions versus natural refrigerants. So as I walk through some of the different regions, think about some of these aspects and these lenses as you view what's going on. And in our transition away from CFCs, it was kind of a different world, right? We had a single universally ratified treaty, which was the Montreal Protocol, and that came about because there was really no argument over the science. There was direct causality between the ozone depletion and the refrigerants that we were using. The other thing was that the industry was very North American and I should say European-centric. The equipment was designed in North America. The refrigerants were produced in North America. So if you affected a change in North America, that technology was exported globally. Now, the amendment to the Montreal Protocol took so long that you now have regional regulations around HFCs, so it's kind of a bit scattered. It's a patchwork. The climate, there's no doubt about that the climate is increasing, but the mechanisms that are causing it are disputed in different countries and by different people. So that causality, that direct tie is sometimes blurred by people's understanding or people's opinions on what's going on. And our markets have become globally diverse. There's half of the refrigerant that's produced now is produced in China. So that market has shifted. Your manufacturing is no longer manufactured in the US and in Europe and exported globally. You have manufacturing all around the world. So there's region-specific manufacturing and designs that are occurring. And that's made it a much more complex change to now transition out of out of higher GWP refrigerants into lower GWP ones. So how much of the global greenhouse gas problem are F-gases? If you look at, and this comes from the United States EPA, if you look at the greenhouse gases, 76% of greenhouse gases is CO2 emissions. And CO2 emissions are really tied to industry and economy, right? So these are the fossil fuels. These are the result of economic activity. So burning of fossil fuels, cars, those kind of things. It's difficult to regulate those because without impacting economic activity. So there's a lot of pushback in reducing CO2 emissions, and it's difficult many times for regulators to make a lot of movement forward on that. Methane. Methane comes from bio-type activities. So you have it from biomass, rotting. You have it from cattle, livestock, people. There's a lot of emissions, and it's very difficult to reduce those. Nitrous oxide, a lot of those emissions come from farming activities and the use of fertilizers. Again, that's a very difficult activity to curtail, especially as the world population grows. So you get to F-gases, and it's only 2% of the total emissions. And if you look at that 2% and you break that down, about a third of that is from foam blowing. Foam blowing is a very emissive activity. As you blow foam out, it's released. Also, the refrigerant that's trapped in the bubbles in the foam comes out over time. A third of it is solvents and propellants. Again, that's a very emissive activity. It basically, as you use it, it's released. And then the last third of it comes from air conditioning and refrigeration. So of the 2% of global warming gases, a third of that 2% is really the activity that we're involved in. And you say, well, how does that break down? What are the most emissive air conditioning and refrigeration activities? And so if you take that 1/3 of that 2% and you break it down, you can see that a lot of the emissions comes from unitary air conditioning systems. And why is that? Well, a lot of unitary type systems are field erected. In other words, they're installed in the field. They don't necessarily ship contained. And when that happens, you have connections that are made in the field. And those connections are subject to, if they're not done properly, to leaks over time. Also, you have folks who are charging and servicing that equipment in the field. And that activity itself can cause emissions when the refrigerant isn't properly reclaimed or properly charged in a way that prevents emissions. Commercial refrigeration, and this is particularly in large supermarkets, whether it's in Europe or the US or regionally, commercial refrigeration type systems are usually distributed. So you have a bank of compressors and long refrigerant lines that feed into refrigerated cases. And those refrigerated cases, again, you have lots of connections in different areas, and those connections are very leaky. And it's been the standard for supermarket operators to just continually charge their units over time. So this is a huge area of emissions. And the last one is motor vehicle air conditioning. If you think about your or your car, really you don't realize that you have a leak until your refrigerant is gone, right? Most of it is out before you realize that there's been a leak in your system. And typically you charge it a few times before you get rid of the car or get it fixed. So the amount of charge in those systems over time is multiples of the number of systems that exist that gets to the atmosphere. And if you look at that, that's 86%, right? That's the majority of the emissions from our from the type of equipment that we use. If you look at the rest of them, transportation refrigeration, that's your refrigerated shipping containers and over-the-road trucks, and that's 8% mainly because of the amount of those compared to the others. But that is definitely an area of improvement, opportunity for improvement. Industrial refrigeration is 6%. The amount of HFCs used in industrial refrigeration is really a small amount compared to ammonia and now an increase in the amount of CO2. So really, HFCs in refrigeration are only used in areas where ammonia is not a good solution. So maybe in a populated area or some other reason that you couldn't use ammonia. Chillers, these are very large charge systems, but typically they're well contained. So the amount of leak rates in chillers and quite frankly, the number of chillers compared to these other systems are much smaller. So chillers are a very small amount of the problem. And then household refrigerators, if you think about those, it's very uncommon for them to leak. They're sealed in the factory. They're usually brazed joints. Where you have emissions from those is at end of life. They don't typically, no one recovers the refrigerant out of those systems. That they get clipped and thrown into a dump, a land dump. So that's really, it's recovery is the issue on refrigerators, not leaking in the field. So it took us a long time, but we got to an amendment in Kigali, and really the success of the Montreal Protocol when it came to eliminating ozone depleting fluids was acknowledged, and what made that treaty back in the 80s and 90s so successful was that it treated the developing world differently than the developed world. There's two different schedules, and there was also funding that was made available through the multilateral fund where developed countries contributed money to help the developing countries transition over time. So that model was used again, and they actually created not just two paths, but actually 4 different paths for transition. There was, and I didn't like the term at the time, but there was the ambitious A5, non-A5 countries, non-A5 meaning developed countries, that had a much more aggressive transition schedule than even developed countries that maybe had some reason that they needed to adjust slowly. And then you had really 2 groups of developing countries. One was kind of the China, the Latin America type of countries that were that are delayed from the developed countries, but they had climates that were typically not high ambient climates. There was an additional time schedule put in for countries that had particular regions that were in high ambient zones, and a lot of that had to do with the transition away from R22, concerns about whether or not there's a good alternative for R22 in the low GWP realm. So the ultimate goal here is an 85% reduction in CO2 equivalent emissions by 2047. So by mid-century, to get to an 85% reduction in CO2 equivalent emissions. And so this is kind of a picture of the different paths. As you can see, the red path is kind of the most aggressive, and then you have the high ambient path being much more stretched out. And the idea there is that technologies that are developed for the most aggressive time schedule will transition and assist those that are transitioning later to get to where they need to be. So again, you can kind of see it's pretty drastic steps, especially in the developed countries. So it's going to create kind of a drive for industry and for regulators to make big moves in those time periods. And as you can see, 2024 is a big date, 2029 is a big date, and then you have some smaller steps as you go for developed countries, and that's basically just shifted for developing countries. So what is our industry? What is our position when it comes to the Kigali Amendment? And we were involved in the negotiation of it, so we're in favor of the transition happening in a practical manner. The U.S. has not ratified the Kigali Amendment, and that's something that I think with the current administration, the Trump administration, there's a lack of desire to bring that forward to the Senate. So as a industry, we've been working through the Alliance for Responsible Atmospheric Policy and AHRI, if you're familiar with AHRI, to try to get the Trump administration to bring it forward. We've also worked within the U.S. Congress to educate our senators and congressmen about the importance of this. And in the last administration, it was painted with the climate this was a opportunity to help in climate, and under the Trump administration, that can be toxic to getting something passed. So we've kind of spun it in the fact that it's important for businesses to be competitive globally where this transition is occurring, to have the U.S. come along so that we can be competitive. So we've kind of changed the spin a little bit away from the environment and more toward business, which is what the Trump administration's more open to hearing about. So we're focused on the importance to U.S. jobs, to trade, for us to be involved and have this ratified. So far that's been a bit of a slow go. There's an election coming up in November in the U.S., and we may see a change in the House, so that might change the way we approach this, but it's something that I just wanted everyone to know that U.S. industry is pushing hard for the amendment. They see it as a very positive thing, and the fact that they've been involved in the process from the beginning has made it something that I think is more practical to happen. One thing that's interesting, the Trump administration is very anti-regulation. They don't want government regulation to prevent business moving forward. But what in actuality is happening, and I'll talk a little bit about this in the next slide, is that the lack of federal regulation has caused our states, the U.S. is a group of 50 states, we're seeing much more state regulation happen because they feel that the federal government isn't doing enough. And so instead of reducing the regulation, we're ending up with 50 different regulations, which makes it very difficult for manufacturers to be able to compete when you have slightly different requirements in every state. So what we don't want to have is a portfolio of 50 different types of equipment to meet 50 different regulations. That's not going to be doable. So that's where I talk about there. Canada, which is also North America, has done a good job of establishing some sector-based transition times. They do have a HFC phase down over time, but there's no real production of refrigerant in Canada. So that it's really all about transition dates being established for certain types of equipment over time. And the one that they've put out so far is for chillers. For January 1, 2025, you have to transition to low GWP options for chillers, which if you look at, I showed you the sectors that are most important. Chillers are probably one of the least important sectors, but that's what they focused on first. It's government, so it doesn't always make sense. So as far as safety and liability concerns, in the US in particular, we're a very litigious society, and some of the alternatives for 410A have some flammability, and that is very much a concern for our industry. We haven't had to deal with that very often in the past. We have in refrigeration, but not so much in commercial air conditioning and residential air conditioning. So that's getting safety standards and codes, and even more importantly, training for technicians is an important thing for us, and that should pace the regulations that are coming out, and that's not the case in all areas. California right now is being very aggressive about a regulation around HFCs, and they're considering dates that are well ahead of safety codes and standards being completed, and that's a problem. We had a couple, the US EPA had a couple of what they called change of status regulations. Their approach to regulating HFCs was actually to remove the approval on certain refrigerants over time for various sectors. That rule was in place, and that was their plan to adhere to Kigali. That actually got challenged in court in the US by 2 refrigerant producers. So this, when I talk about commercial aspects, 2 refrigerant producers that didn't have the most likely solutions sued the US EPA around their rules and their authority to use it, and actually won. So those rules that the EPA was depending upon to affect this change actually got what they call vacated or removed. So that's left a lot of uncertainty in the US. And where 2 years ago we thought we had a plan to get away from HFCs, now there's a lot of uncertainty going on. Yeah, I talked a little bit about A2Ls, and I'll go into that a little bit more, and the concerns about the patchwork in various states. So we don't, we could end up in 2020, as early as 2023, having 2 different rules with 2 different, with like California and some more progressive states having where you have to use A2L refrigerants, and the rest of the country where you don't. And that could be very difficult for us to manage. In Europe, and this is typical of Europe in my experience, is Europe jumped ahead of everyone else. They went too fast and too far, and their regulations actually hurt their own industry. And I was very much a part of the negotiations went on around our European F-gas regulation. They put their regulation into place before the Kigali Amendment had been completed, and their phase-down schedule is actually more aggressive than what Kigali requires. So they're forcing their industry and markets within Europe to go faster than what Kigali is doing. They were a leader, particularly toward the end, in driving to the Kigali Amendment. The one good thing about the F-gas regulation, it has a 5-year cycle of review, so they have an opportunity to tweak it every 5 years. So if it's not working, they can change the way it is. If there's a problem with it, they can change the way it's implemented. The other thing is that although the F-gas regulation is a pan-European regulation, implementation happens at the state level, and the opportunity for individual countries to do something more than what the regulation requires is there. And you see in the Northern European countries that Denmark, Germany, other places are actually going further in banning certain substances than the F-gas regulation requires. So that, again, creates a patchwork of regulations in Europe that makes it difficult to produce product there. They do use sectoral bans, which means certain equipment can't use HFCs after a certain period of time, but those sectoral bans are actually after some of the production reductions, and that's created a lot of problems in Europe where you basically have shortages in refrigerant, and we're seeing in the past 12 months, we're seeing certain refrigerants like 404A and 507 have price increases of 10 times. And even my own company's service operations have trouble getting refrigerant to service equipment in the field for our customers. So it's created a big problem. They also, the way they manage production is through allocations, basically credits on how much a producer can use or to make. And those credits have, they get given to producers, and those producers can use them or even sell them to other producers. And that's created a third-party market. You have actually people who don't use refrigerant and don't produce it, who are trading these allocations back and forth, and that's driving the price up of those. So that's something the EU needs to fix. And I talk about how they hurt their own industry. In the EU, if you import refrigerant into Europe, like if you have pre-charged equipment that you're importing into Europe, you have to purchase allocations for that refrigerant. That makes sense, right? They have to be able to manage refrigerant coming in. Unfortunately, they don't give you credit if you make equipment in Europe and you export it out. So manufacturers that make equipment in Europe who want to sell in the Middle East, for instance, are burdened with the cost, that extreme cost of refrigerant. So they've actually, the way they've set up their regulation, they're hurting their own industry in exports outside of Europe. So the idea, I think, was to try to further restrict the amount of refrigerant used, but what they've done is really made it harder for those companies that exist in Europe to compete outside of it. And that'll just drive manufacturing to other places. China is very thoughtful in their approach, and they're very concerned about protecting their native industry. So as I mentioned, about 50% of the refrigerant that's produced is produced in China, and their regulations are really aimed to try to protect that industry and their manufacturing in China. So as far as the type of refrigerant low GWP options they're looking at, they want non-proprietary ones. So R32, which is a major component of 410A, is a non-proprietary refrigerant. And so there's a push toward R32 in a lot of equipment. Also the use of, in small charge devices, propane, isobutane. So in refrigerators and small split systems and through the spot coolers, those kind of things, they're really pushing for those non-proprietary solutions. One thing that they've been slow to move in, and they're doing a lot of research on the safety aspect around flammable refrigerants, but they seem reluctant to put out a safety standards ahead of an ASHRAE or an ISO standard. They're kind of waiting to see what comes out. So even though there's a lot of R32 equipment being produced in China right now, that's all for export. They're not really selling any mildly flammable refrigerant-based equipment in China at this point. So they're taking their time, and they're very concerned about making sure that whatever happens, their industry isn't disadvantaged. India in the Middle East, and this is where the R22 is still a big issue. We're just getting started looking at the transition to low GWP refrigerants. They haven't fully exited R22. The idea is that do they go R22 to HFCs and then have to transition again to the low GWP refrigerants, or do they skip a step and go straight from R22 to these low GWP options? And what assistance are they going to get from the Montreal Protocol to do that? You know, are they going to get an opportunity to, for help in that transition twice or just once? And if it's just once, they absolutely want to go to the future, not an interim step. So we're seeing a lot of kind of pushback initially on the Kigali Amendment from places like Saudi Arabia and Kuwait, basically the GCC countries. And they're, you know, a lot of what they were looking for was that assistance from the Montreal Protocol multilateral fund, which is that money fund I mentioned, and also a later transition and possibly some relief on their requirements to get out of R22, a little more time in R22 in order to make that transition to the low GWP refrigerants rather than having to immediately get out of R22. So the other thing that's happening, and I think it's true here in Lebanon, energy efficiency is an extremely important issue, and not just because of climate change, because of stability of their grid, right? So we're seeing, you know, in Saudi Arabia, there was recently a study that shows that by 2030, they could be a net importer of energy because of their current energy use. So there's a big focus right now on improving energy efficiency across the board, and that's certainly something that we're seeing, you know, part of what their consideration is on this equipment. The other thing is technicians, especially as you get into the mildly flammables. You know, the skill level in technicians across the Middle East isn't uniform, and there is a lot of concern about folks getting hurt when they're servicing equipment if they're not trained correctly, especially in the use of flammables. And right now, there's not a lot of experience that exists, even in developed countries, in the use of them. So there's a lot of concern about developing training courses. And one thing that you're seeing with ASHRAE is cooperation with UNDP to develop, UNEP, to develop training programs and information programs around mildly flammable refrigerants and proper servicing techniques. Japan, again, is a very thoughtful approach, and they have really used, and what I think is extremely important, is they look at not just new equipment as their area of focus, but also requirements to do leak checks and to make sure that the existing equipment in the field is being focused on, because that's where your emissions are coming from. But only about 3% of the total HVAC equipment is new every year, right? So if you're going to make an impact, you need to reduce the amount of emissions that are coming from existing equipment, and their programs have mandatory leak check requirements. Europe has a portion of that too, but that really is an area, if you're going to make an impact on refrigerant emissions, you need to focus on existing equipment, and that requires you to require building owners, not manufacturers, to do periodic maintenance and make sure that their systems are running correctly. So they have an overall target of reducing emissions by 50% by 2025, which is pretty aggressive. They were one of the earliest adopters of a regulation in 2015. They look at not only production of refrigerant and use of it in equipment, but also recycling that refrigerant and ultimately the destruction of that so it's not leaking out from storage tanks into the atmosphere later on. So they really have a comprehensive life cycle approach to their regulation, and they've done a lot of research around the use of A2Ls, R32s being used pretty commonly in Japan, and they've done a lot of work on what is safe charge sizes and various types of equipment. So really the lessons that we've learned with these early regulations are that safety standards and building code updates and in particular training of installers and service technicians must occur prior to a transition date. And that's something that as other countries look at developing HFC regulations, they got to make sure those things happen first, or there's a pathway for those things to happen first. Refrigerant management provisions, this is the making sure that existing equipment isn't leaking, has the greatest impact on the total, a reduction of total emissions. So you need to make sure that that equipment is being checked periodically and that you're stopping emissions early. Allocation-based production phase down must be tightly managed, and this is kind of a reference to the European model. If you're not managing how the reductions go over time, you could end up with spikes in prices and having shortages of refrigerant for use on existing equipment that it's in the field. So that needs to be tightly managed and controlled. If you go faster, like Europe has, you end up hurting your own manufacturing, your own company, or country. So it's important that you make sure that you are cognizant of what you're doing to the industry as you go forward. You can't base triggers solely on GWP. Energy efficiency is important, and I'll talk about that in a minute. Consistency, the more consistent the regulations are across various countries, the easier it is for manufacturers to comply. So we don't want this patchwork effect. Regulators typically don't understand the science and the engineering around this equipment, so you don't want them picking winners on which refrigerants to use and not. Let the industry help you decide. And then sectors with the greatest impact should be addressed first. So focusing on chillers first doesn't make sense. Focus on commercial refrigeration, focus on the small unitary type systems. That's where you'll make the biggest impact first. And then lastly, and probably most importantly, safety risks and transition costs should be proportional to the benefit to the environment. So you look at the amount of global greenhouse gas emissions that our industry is responsible for, make sure that the costs and the timing of the transition is proportional to the improvement to the environment. So I'm not saying we shouldn't do it. We absolutely should do it. But being extremely aggressive doesn't make a whole lot of sense when you look at the total emissions. Okay, so that was the slow part. So I apologize for that. I'm going to talk a little bit now about safety codes and regulations. If you are familiar with ASHRAE Standard 34, Standard 34 in ASHRAE is actually the standard that gives refrigerants their R number, so like R134A. That comes from Standard 34. And not only is it given a number designation, and there's a whole methodology around how that number is determined, but it also sets toxicity and flammability parameters around every refrigerant. So if you look at R134A, for instance, it is from a toxicity standpoint, an A, which means less toxic. B is more toxic. And it is a 1, which means it's non-flammable. It doesn't have flame propagation. A refrigerant like propane is an A3, meaning it's lower in toxicity, but it has a high flammability propagation. And what's new is this A2L. And what that is mildly flammable. And I always get kind of a chuckle from folks who aren't in our industry when they say, what do you mean mildly flammable, right? I mean, it's either flammable or it's not. And it's been explained to me that really mildly flammable means that the flame propagation is slow. You could outrun the flame. Well, that doesn't make me feel any better. It's still flammable, right? So it also has a low energy of ignition. So the pressure wave that occurs when it ignites is much less than a propane or an isobutane. But the bottom line is that it's not the same as an A3, and the techniques that we use to use it and mitigate the concerns are not as extreme as they would be for propane and isobutane. So the idea was that our industry needs to handle A2L refrigerants differently than they do a propane or an isobutane. So ASHRAE developed this category of A2Ls and has started to apply that to various fluids. But standard 15, the safety standard that applies to equipment rooms, hasn't, to date, hadn't put any provisions in it to handle those A2L refrigerants. It handled them as a class 2 or a class 3. That's an effort that's going on within ASHRAE right now, and there's a lot of research going on with the low GWP MTG to develop methods to use A2L refrigerants safely. And when you look at the different types of equipment, how you handle a mildly flammable refrigerant in a water chiller, which doesn't have any direct refrigerant coil in the airstream of a building. You have a secondary loop that has water in it. That's very different than handling a coil in a split system that's directly in the living space, or a coil that's in a duct that is, being blown through the building. So the application of a air-cooled chiller that's sitting on the roof of a building, the safety mitigation techniques that you have to use for that are much less than a split system. So what we're seeing is really it's based into 3 categories: units that are outside, units that are based in an equipment room, and those 2 being indirect systems, right? So chillers, other systems that have a secondary loop between the living space and the machine. Those transitions are happening more quickly than ones where you have a direct coil, like in residential or commercial split systems, where you have coils directly in the living space. And so in the past, standard 15 didn't really have a difference between those types of equipment. Now there's actually a separate, what they call it, ASHRAE 15.2, a separate section or appendix within 15 that'll deal with that equipment in split type systems. So I know this is a busy chart, and I don't expect you to really take much out of it, other than we're handling as an industry outdoor chillers in mechanical rooms, and unitary and residential systems separately. And the work that needs to be done for outdoor chillers to use A2L refrigerants is basically complete. The chillers in mechanical rooms, the ASHRAE part of that has been updated, and there's a UL standard, UL 60335-2-40, that has been completed, and we expect that 15 in the 2019 revision will have what's needed to be in that standard to handle chillers in equipment rooms. And basically that's a refrigerant sensor and some means of venting the mechanical room, right? So which in many cases already exists. So it's a couple holes in the wall and a sensor to make sure that it turns the fan on when you need it. What isn't shown here, and I'll talk a little bit about it after this, but once you update the ASHRAE standard, that's only a part of the story, right? The building codes, whether they're in the US or anywhere else, have to call the most recent standard. So those need to be updated. And then those building codes that call out those need to be adopted by the local jurisdiction, whether it's a country or a state or a region, right? And then unitary and residential, the 3rd edition of 60335 is the one that's going to have great implications to equipment design. That's still a work in progress. The expectation is that it gets done in late 2020. That may not occur, depending on the research that we do and what we find. This is the most important piece, right? This is where these are systems that are field erected, where leaks can occur. Finding a way to prevent bad things from happening is extremely important, and that's why there's a lot of industry effort around that. I have those in yellow because I'm not confident that those dates are going to get hit. So in the best case scenario, we could have ASHRAE 15 updated by 2023. Everything has to happen just right to make that happen. Otherwise, it would be a later version. And then the building codes, again, have to adopt those, and so that can push things out. Whenever we negotiated the Kyoto Amendment, the 3rd step down, which we felt was where unitary equipment had, basically 410A had to be transitioned, we pushed to 2029 because we felt that was a much more practical date for that to happen. So that was one reason that step down for developed countries is at 2029 versus earlier, because we wanted to have time to get the safety codes and standards figured out. So as I mentioned, our industry, you know, we can work on the ASHRAE standards, standard 15 and ISO standards 817. We can work on those. We have an ability to accelerate those and getting updated. And the building codes itself, where we haven't typically played as an industry, we're getting involved to push things to the building codes. How those building codes get adopted in various countries and in states and regions, that really depends upon the government making some push to get things updated more quickly. And that's where we've had a lot of discussion in international meetings and with governments to say, you guys need to step up to force your local jurisdictions to update these codes if you want to do the refrigerant transition. And that's something that hasn't always happened. They're not sure how to approach that. So what carrot or what stick do you use to get local jurisdictions to update building codes? And oh, by the way, building codes have a lot of other stakeholders that have nothing to do with refrigerants. So home builders, insurance companies, others that may have a different view than we do about, you know, this refrigerant change. So as I mentioned, governments have the greatest influence on that piece of it. Industry has an opportunity to accelerate things on this end of it. So what are we doing as an industry to accelerate the updated codes? Well, one thing that ASHRAE and AHRI, and with cooperation with the US government and California, have actually put a big pool of money together that ASHRAE and AHRI are doing specific research around low GWP refrigerants, and in particular, the safety aspects of using those in various types of equipment. So AHRI put in $1 million. ASHRAE took $1.2 million out of the reserve research fund to put into this. The US government, this was back in the Obama administration, had given $3 million, and California put $500,000. And I'm proud to say my own company donated $100,000 to this effort too. So the idea is that we want to make sure we have good information to develop safety codes and standards that prevent people from getting hurt in using these new refrigerants. And the other things that are very important, as I mentioned, technician training. We got to put work into developing knowledge around how to use these, and so folks don't get hurt while they're doing it. Okay, so that's kind of safety codes and standards and regulation. So it's a bit dry. I apologize for that. I'll talk a little bit more now about what the importance of energy efficiency is in the choice of the refrigerants that you use, and in particular, the impact of energy efficiency on the total emissions of equipment. This is the takeaway. The dominant contributor to greenhouse gas emissions from the equipment that we use and make is the energy that it consumes over its life, not the refrigerant that it contains. So if you take, and this is an example of a chiller, or well, I guess in all equipment, a chiller is actually even more extreme. 90% or more of the emissions in CO2 equivalents from a HVAC and R piece of equipment over its life come from the energy that it uses, and only 5% if you lost all of the charge that it contained. So what are, you can kind of put these in two different categories. Direct effects, which are the refrigerant itself, and these are gradual leaks that occur during normal operation. An event that you have maybe a line break and you lose all of the charge, or loss at the end of life when someone doesn't properly recover the refrigerant that's in the unit before they get rid of it. So this is the service technician clipping the line and letting the refrigerant go out before he takes out the unit. Right? So those are direct factors. Indirect factors are operating conditions, so different, in different regions with different applications within a region. your units can operate at very different conditions. So when you have high lift, high ambient conditions, or a large load, you can have a very different energy use pattern than you have with a system that runs in a lower ambient condition or less load. So important things that affect are the efficiency of your motors or your compressors, the amount of heat exchanger surface that you use. That can all have an effect on energy efficiency. And then the type of power that you're using. You know, if you're using a renewable source to get your power, then the effect of indirect emissions can be much lower. So if you're tied to a nuclear power plant or to a solar array or to wind turbines, you know, the energy use is a much less component. But if you're, you know, like in the US and in Europe, there's still a good number of coal-fired power plants, and in particular China, where they use almost exclusively coal. That can be a very dirty operation from a CO2 equivalent standpoint. So kind of, again, this is a different way of looking at it. Direct emissions are the refrigerant itself, of course, the equipment leakage rate, operating life, refrigerant charge, and reclaiming and recycling. And we have an obligation as designers of equipment and users and servicing technicians to try to reduce those as much as possible. Indirect emissions really are around energy consumption. Some of that we control, how efficient is the equipment that we build and spec, and then some of it is with the way the power is generated. What is the emission type factor? Emission factor is really kind of how dirty your power is, and then the equipment operating life. How long are you using that piece of equipment, and are you maintaining it well? So this is just to give you an example. If you look at, you know, how much is indirect versus direct, this example is a chiller. And I kind of did two scenarios here. One, if you poorly maintain it, in other words, your leak rate's high and maybe you're not using your energy or keeping it maintained to keep your energy use correct. But you can see that in a chiller, 98% of the emissions over the life of the unit come from the energy that's used. You know, even in a poorly maintained situation, it's still 90%. So that's a big lever on energy efficiency. What is our focus? It's on refrigerants, right? So what should we be focused on? Energy efficiency, right? So to kind of put that in a different perspective, if you did a trade-off, if you're buying a chiller and you want to spend your money either on surface, in other words, improving energy efficiency, or you want to spend it on getting a low GWP refrigerant, for a 1% improvement in chiller efficiency, you could offset 63% of the charge on a 134A unit. And for a 1.6% improvement on chiller efficiency, you can offset the total impact of the charge that's in it. So what the takeaway from this is, if you want to be green, buy the most efficient chiller or piece of equipment you can get. And that's what I tell our customers, right? Now, the other implication of this is, if you choose a low GWP refrigerant, it better be more efficient. Because if it's not, you're going backwards, right? Because that leverage, it works in the opposite way too, right? If you have a low GWP refrigerant but it's less efficient and you don't offset that by more surface, you're actually emitting more to the atmosphere than you would otherwise. So what do we do as refrigerant as equipment manufacturers? How do we choose which ones we use? Well, we absolutely have to look at safety and reliability of our units, right? Our customers expect a 25-year life on a chiller or a 15-year life on a split system, and they're not going to accept if we put a refrigerant in there that's not stable or not reliable and our unit fails in 5 or 10 years. That's not going to be acceptable, right? So it also has to, of course, meet regulations around efficiency and sustainability, right? So, you know, are the indirect effects of our refrigerant and the efficiency of our equipment has to be there. And the other thing that's important and not always considered is the refrigerant refrigerants that we use have to be affordable, right? That 10 times increase on refrigerant cost is not going to be acceptable to the marketplace, or it'll force people to take compromises on energy efficiency in order to buy their unit. And it has to be available. Some of these refrigerants that are being touted by the producers are not available in large quantities yet. So that makes it very difficult to transition in certain regions because you can't get access to the refrigerant. And kind of if you look at the different, and this is, I'll do this fairly quickly, what are the alternatives that are out there for us? Well, you have to kind of consider that there's kind of 3 types of equipment and compression devices. And kind of the higher in capacity you go, the more efficient your compression device needs to be. So, usually in small capacity, small charge systems, we use scroll type compressors. Those are less efficient, but they're compact, and you can get a good bit of capacity in a small package, right? So those typically use higher pressure type refrigerants like 410A. As you go up in capacity, you can get into screw chillers and small centrifugals. Those we call mid-market or medium-sized chillers. And that, right now, the refrigerants that are used there are usually a 134A and 513A, which is a low GWP refrigerant. And then as you go to very large capacity systems, you typically go into a centrifugal type chiller. And there you can have medium or low pressure type units. And there's some that are currently in the marketplace listed there. So what are our, I think I might have gone one too far. Okay, yeah. So what are our options? For 134A, and I'm going to explain this chart to make it easy for you to see. This baseline, it's all relative to 134A. That's my nexus. That's my origin there. This is capacity versus 134A, and this is efficiency versus 134A. So if you are just as efficient as 134A and you get the same capacity, you're right on that X, right? So if you're more efficient, then you're above the line. If you get more capacity out of your option, then you're further to the right. Okay, so where you would love to be is up in that upper right quadrant, right? So if we had a perfect solution, we'd be more efficient and get more capacity out of it, right? What you see here is, this is for centrifugal type machines, our alternatives are either low pressure or they're around the same pressure as 134A but lower in efficiency. Lower pressure type options have much less capacity. So how do you fix that? Well, you either get a bigger wheel on your centrifugal or you spin it faster, right? So some of the alternatives that you see out there, R123 is there for a reference. R123 is actually an ozone depleting refrigerant that's being phased out. But you can see that there's some different alternatives. And 1233ZD and 1336 are 2 that we're seeing used quite often. There's another one, and it's very close to 123. It's 514A. It's that little triangle by 123. That's being used as a drop-in for 123. So it's not on there, but it's I see that kind of as a specific use to transition 123 units. I think longer term you're going to see 1233ZD in low pressure units. But one thing about low pressure units, when you get into very large capacities, 2,000 tons of refrigeration and greater, those units get huge, right? So what we still see is that there's quite a few R134A type units out there, and there are alternatives for 134A, 513A being one of them. But what is the problem with 513A? It's less efficient. So if you don't adjust the surface that you use to get back to that same efficiency level, you're going backwards. So as long as you can use 134A, I would use it and buy as much surface as you can. When 134A is no longer available, then 513A will probably be the alternative that folks use, and that's going to be something that you need to adjust your level of efficiency, and it's going to cost more. What's that? Ammonia, and for centrifugal chillers, we typically use it in screws. And actually, I'll talk about that. Again, there's nothing up in that quadrant for 134A, okay, for medium pressure. Yeah, I'll talk about that. So that's not good. That didn't come through. I'm not sure what happened there. Okay, I apologize. Not sure what happened there. All right, so I'll try to, let me go to the next one, maybe we'll go back. Okay, for scroll compressors, all right, 410A is here. What do we have? We have some up in that quadrant, right? We have some that are better in efficiency, and we actually have ones that are better in capacity too. What are the problems with those is that orange dot means they're flammable. Okay, so the alternatives that you have for 410A that are practical, ARM32 is one that has a significant reduction in capacity, which makes you have to make much larger systems. The ones that are really available to you are the ones that are shown there. And those are the ones, R32, that's a focus of some manufacturers. R454B actually there's a label there that should be A and B. Those are ones that are being considered. Again, they're A2L flammables. We're going to have to deal with the flammability for scroll-type compressors. For screws, it doesn't show on here. There are some alternatives, and I'll maybe talk through them, and I'll apologize. I can see it on the screen. I'm not sure why it's not projecting. But your alternatives, many screws are 134A. Some screws are 410A. So the alternatives for 134A is 513, as we talked about. There is a 1234 ZD, and that one has some flammability to it. So there are some air-cooled screws that are going to use that refrigerant, and we're seeing that happen in Europe. So that is an alternative. The good thing about screws is if you need to make up for capacity, you can spin them faster, or you make the screw longer. So that is an opportunity. There's a lot of variable speed screws now that you can overspeed them. There are some limitations to that in the machine dynamics, bearings, and things like that, but that is an opportunity for us. Other than those two, I think you did mention ammonia. Ammonia is an option for screws, and my own company makes ammonia chillers. They're screw chillers. The problem with ammonia is it is toxic and it is flammable, right? So you have to have specific applications that make sense. And so maybe if you have an equipment room that is separate from the occupied space, then you can do that. But it is very specific. Okay, so the refrigerant landscape, again, there's two focuses that we're seeing, kind of drop-ins. What can you just put directly into 410A equipment, in other words, to use, or replacements for 134A. And then you have refrigerants that are slightly different and require manufacturers to do optimization. Some of the mixtures that we see have what's called a glide. In other words, when they evaporate over a range of temperature rather than at a single point. When you have that, that's an inefficiency in your heat exchanger that you have to make up for. Again, more surface, more cost. I'll give you this chart as kind of an idea of what's out there right now in the industry. 410A, I mentioned 32 and 454B are really the alternatives for that, and those are going to be dependent upon the safety codes and standards. R134A, you're seeing 513A, which is a non-flammable. That's basically a drop-in for 134A. 1234ZE, as I mentioned, is a mildly flammable, and we're seeing some of that used in air-cooled equipment. R22, there really isn't a good drop-in for R22. So that is still a concern, and that's why many countries that use R22 still are kind of wanting more time. And then R123, I mentioned, is going away. 514A, I mentioned, is a drop-in for R123. 1233ZD is not. 1233ZD has a higher pressure, and it means the vessels have to be code. So they have to be under the mechanical code. So that you can't drop in 1233 ZD into 123 chiller. You have to make a dedicated new system. So, yeah, the other thing, just quickly, there's other things that we can do as manufacturers, like have heat exchangers that don't use as much charge, like microchannel or falling film evaporators. There's improvements that we can do using, different types of systems, mag bearings where you don't need an oil system that reduce leaks, things like that. So there's things that we're doing as an industry to help not just look at new refrigerants. So those are our key takeaways. I can take any questions if we have time for that, and I apologize for running a little long.
I think, energy efficiency would be of interest. Is there any question from the audience? We're kind of running out of time. Bill is going to be around for the break, so I'm sure that he could entertain some questions.
Yeah. I have only one simple question. R32, I came to know that Daikin, they are trying to market.
Yes.
But I asked yours also, they have not replied to me. So is it suitable for your centrifugal chiller? Hello?
Yeah.
Because I discussed with the Daikin regarding that refrigerant R32. So they are telling very soon they should be in the market for the R32. I think so it should be applicable for the scroll chillers or something like this.
Well, R32, for scroll chillers, if you're talking about a chiller that's air-cooled,
I don't know. They told me they are going to market R32 with the chillers.
if it's an air-cooled chiller that uses a scroll and it's sitting outside, then if you have a leak, it goes to the atmosphere. You don't have an opportunity to concentrate that into a flammable mix. So I think R32 or 454B or any of these mildly flammable in an air-cooled chiller standpoint are probably fine. When it comes to a water-cooled chiller where it's inside an equipment room, then you have to make provisions to vent that equipment room in case of a release. So you don't want a flammable mix.
No, my point is that in the plant room always it should be vented. That is not the issue. Even your standard 134A also we vented out the plant room. Yeah, true. But my point is for the new kind of refrigerant which is suitable for your chiller, what you are designing, thinking for the next generation.
Right. For 1233 ZD or those type. The thing that's important to remember when it comes to low GWP refrigerant, they're low GWP because they break down quickly in the atmosphere, right? They don't ever get to the upper atmosphere where they can affect the ozone layer because they break down very quickly. What that also means is that they can break down very quickly in your system if you don't maintain it well. So it's very important, and what takes the most time for our manufacturers is to do the reliability testing around these refrigerants to make sure we're not creating a problem 10 years down the road or 20 years down the road in our equipment because of breakdown in reliability.
Now my next point is that the new generation chiller, the dimensions for the same tonnage, dimensions should be larger?
It depends on the refrigerant. For low pressure refrigerant, they'll be larger. For medium pressure, it should be about the same.
Yeah. I think we could take the question probably out of the break and then we could explain more. I'm really sorry for not taking questions. We're kind of running out of time. Bill is going to be around for any questions you may have during the break. So I would like to close this session. Thanking Bill for all the effort that he did.
Thank you.
Please note there is 2 other sessions in parallel. Will be starting at 11 o'clock. So coffee break will be served outside. Thanks so much for attending. Thank you.